In this video, we will talk about graphs of functions. To begin, let a and b be sets and let f be a function whose domain is a and whose codomain is b. The graph of f of x is defined as the following set: the set of all ordered pairs x and f evaluated at x, where x is an element of our domain a. It is standard to look at ordered pairs like this and associate the left coordinate with our input and our right coordinate with our output. The traditional way or common way of doing this is to let the left coordinate be our x coordinate for a graph and the right coordinate be our y coordinate for a graph. To see an example, let f be the function from z3 to z3 given by f of x equals x plus 1 mod 3. First, we need to draw the grid. The horizontal line, or our x-axis, will display all values in the domain, and our vertical line, the y-axis, will denote all elements in our codomain. We will graph the function by evaluating each value on the x-axis and fill in the corresponding square. F evaluated at 0 equals 1 mod 3, so we will fill in the square 0, 1. F evaluated at 1 mod 3 equals 2, so we fill in the square 1, 2. And finally, f evaluated at 2 mod 3 is equal to 0 mod 3, so we will fill in the square 2, 0. And this is how you graph a finite valued function like the one here. In this next example, we will plot a graph from a given table. Consider the table of x, y values. We will consider the x values as input to a function and the y values as output to a function. So we can see that 1 will be mapped to 2, 2 will be mapped to 2, and so on. Start by drawing our axes and labeling all the values in our grid. We can see that the x value of 1 has a corresponding y value of 2, so I will fill in the square 1, 2. And in a similar fashion, I will fill out the remaining squares using the corresponding x and y values. This next example serves two purposes. We will be given two functions, f and g, and we will use the graphs of f and g to see that these functions are actually equal. As we saw in a previous slide, we can compute the graph of a function by evaluating that function at every value in its domain. Let f and g be functions from z5 to z5, where f is defined as x plus 1 mod 5 and g is defined as x minus 4 mod 5. By evaluating f at 0 through 4, I obtain the following values. To get its graph, I will draw my axes like I've done before, I will make a grid, and I will start filling out all of the corresponding values. That is, since f evaluated at 0 was equal to 1, I would fill out the square 0, 1. Since f evaluated at 1 was equal to 2, I would fill out the square 1, 2, and so on. I will repeat this process for the function g. Here is the following set of inputs and outputs for g, and just like before, I will graph it in the exact same way. F and g are functions that are defined differently. With f, I add 1 to each input, and with g, I subtract 4 from each input. But even though the arithmetic is different, the graphs of the functions are the same. This tells me that f and g are actually equal as functions. In this next example, I will attempt to deduce a function just from its graph. Consider the following graph, where my x-axis goes from 0 to 4 and my y-axis goes from 0 to 4, and I have the following squares filled in. From this, I can fill out an xy chart, or an x f of x chart if you like. Virtually, they are the same thing. Given the x and y-axis of this function, I can deduce that I have a function from z5 to z5. My goal now is to see if I can deduce any kind of pattern from this. 0 gets mapped to 2, 1 gets mapped to 3, and so on. It appears that what I'm doing is taking each input and adding a 2 to it and modding out by 5. Just by examining this with a couple of examples, we can see that 0 plus 2 is 2, which agrees with the input and output relation. 1 plus 2 is 3, which also agrees with the input and output relation. And 3 plus 2 is 5, which is 0 mod 5. Again, that also agrees with the input and output relations that we're seeing. This means that I can deduce that my function f of x is equal to x plus 2 mod 5. In this next example, I will get information from a graph. Consider the graph whose x values go from 0 to 4, whose y values go from 0 to 1, and where the following squares are filled in. Using roster notation, we can list the set of ordered pairs of this graph. I have the square 0, 1 filled in, so I will write down the ordered pair 0, 1. Similarly, I have the square 1, 1 filled in, so I will do the ordered pair 1, 1, and so on. Using the x-axis, I can determine that the domain of this function is the set 0, 1, 2, 3, 4. Similarly, by using the y-axis, I can determine that the codomain of this function is the set 0, 1. Notice that I wrote an f next to the graph. That means that this is the graph of a function that I am calling f. So if I want to use function evaluation notation, I can use the coordinate 0, 1 to say that f evaluated at 0 is equal to 1. Likewise, the coordinate 1, 1 tells me that f evaluated at 1 is equal to 1, f evaluated at 2 is equal to 0, and so on. Then I will compute the image of this function. In other words, I'm going to compute the set f of x, where x runs through all values in my domain being z5. The image happens to be just the set 1, 0.